Hello everybody and welcome to another episode of Light Dark Academy. My name is Giuseppe Improda and today we are talking about linear and non-linear workflow. Today I will do something a little bit more interactive to make these kind of videos that are a little bit technical more easily watchable. So I have a blank Photoshop canvas here and I'm gonna fill it up with elements that I think will be helpful for explaining the concept that we have to talk about. So hopefully this makes things a little bit more interactive and you don't fall asleep while watching the video. So let's get into it. Nonlinear workflow comes from a legacy problem. That was the gamma correction used or necessary in CRT monitors. So this is our CRT monitors. Now some of you are older, some of you are younger, maybe you have never seen one of these monitors in your life, which is good for you because it means you are very young. But these were CRT monitors that obviously are not flat as the LCD monitor that we now have, and actually they were pretty big, huge, heavy and cumbersome, and thank God they're gone. These CRT monitors though had another problem aside from the size and the weight, which is that the signal was not linearly related to the brightness of the pixel on the screen. To explain you this concept, I want you to understand first what a linear and non-linear relation between two terms is. So let's get into a little graph here. Let me brush it out. So let's say that these and these are my axes, right? So this is y and this is x, and this is the origin where everything is 0, so 0 and 0. Let's say now that I have two terms, one on y and one on x, and this, for example, if I trace a diagonal line here, which is cutting this quadrant, I will have one here and one here and two here and two here and three here and 3 here, and 1, 2 and 3, this distance and this distance is exactly the same, so that if I intersect these points like so, basically this distance between 0 and 1 and 2 and 3 is always the same, which means that both terms have increased the same amount. To explain that in an even simpler way, we can think about a staircase, for example, right, where every step has the same height and the same depth, so that they are all regular. This kind of staircase has a linear relationship between the number of steps and the height, because at each step, let's say like this, corresponds an increase in the height of the total staircase. So step 1 has this height here, let's say that this is 10 centimeters, just to say a number. Second height, we will have the step as 10 plus 10, which is 20 centimeters, and so forth and so on. So there is a linear relationship between the number of steps and the height. And so on the x we could put the number of steps, for example, so we can write here steps, and on the y we could write the height, where, for example, we would have 10, 20 and 30 centimeters. Every time we increase the first term, there is an equal amount of increase in the second term. So the result is that we have these points here, and the curve that we get is actually a line, right? Is a straight line, and that's why it's called linear, because it's a line. Now let's go back for a little bit, and let me actually delete this whole thing and throw it again like this. Now, what happens if the relation between the first term and the second term is non-linear? Which means that, for example, in the staircase example, we don't have all the steps of the same height, but some of the steps are higher. For example, some of the steps are lower at the bottom of the staircase, and some of the steps are higher, taller at the end of the staircase. So we would have something like this, for example. right? So this is not a linear relationship anymore because we don't have the same amount of value increased every time we have a new step, but instead this is a non-linear relationship. So in this case we would have step 1, 2, 3, 4, 5, and 6. 1, 2, and this time our increase in height is different. So let's say that this is 10 centimeters, the second one is 10, 12, the third one is even more, let's say 15, and the fourth one is actually 20, and then the fifth one is 30, and the sixth one is 50. So when I bring these values on the intersection line between the two terms, so in this case this is 6, we get a point here, then we have 30 at the fifth step. So now if I connect these points, I get something like this, which is different from the actual linear line that we had before. So this is not a linear function anymore. So all this to explain you what a linear and a nonlinear function is. So when you have a function that instead of being like this weird curve that I draw is like this, let me delete another one and make it again. And you have a curve that is like this, that's a bit excessive, like this, right? You have a gamma function, so that has this sort of result when you connect the two terms in the y and in the x. I don't want to get too much into the functions of things here, into the math of things. I want you to understand the concept of what is a linear graph versus a non-linear graph, and hopefully the example with the steps helps you with that. Is important because in this situation, like when you have a linear function, the mid of this line, let's say corresponding to these 2 points, let's say that is this one, and this is basically coming from this midpoint here, corresponds to obviously the mid value of the other term. But when you have a nonlinear function, let me change the color here, like this one, right? This mid value here does not correspond anymore with the other mid value. In other words, if I take the same line here, you can see that now this one corresponds to this point, which is much higher than the mid value there. And this is where things get tricky, because it means that the relation between the first term and the other term is not linear, and hence there is a difference between the way one element is increasing versus the other one. And this is where our friend here, the CRT monitor, had a problem. With CRT monitor, the amount of energy needed or electricity needed to generate dark pixel and bright pixel is not the same. So you need more energy to generate brighter pixels, and that's why the relationship between electricity and brightness of the pixel is not linear, but is a non-linear function and is actually the gamma of the monitor. We put here, and this is our CRT monitor gamma 2.2, which has this sort of slope, this sort of graph. And as you can see, it means that you need a different amount of electricity to drive the brightness of the pixel, according to if the pixels are dark or bright. And this is why, let me delete this, we need another curve here to counterbalance this problem that this CRT monitor has. And have the monitor defect curve, which is this one, and we times with another curve that we define, which is our sRGB, in this case gamma 0.5. We are getting there in 1 minute, and this will give us the linear image displayed on the screen that our eyes can then interpret and understand. So now all these problems don't exist anymore, because now with our LCD or LED displays, they are fully digital, so they do not have this gamma 2.2 problem of the monitors. They don't have that kind of issue. So they are linear in the relationship between the signal that they have and the brightness of the pixel. 100% bright pixel equals to 100% signal needed to give that brightness. And so if you apply half the current to 100% bright pixel, you will have a 50% bright pixel. There are other media that don't have the linear response that we are talking about. Like, for example, the film itself doesn't have a linear response. Let me open an actual, and this is the response of the film. So you can see that the relationship is not linear, but is actually this S curve, which is also known as a log curve. All right, so now I don't want to get into the film response to the light, to the exposure, but it's clear that you have the brightness or the exposure of the film and the density of the film itself, and these two things are not linear, are not working the same way. So you need different amounts of light for the different density of the film, which translates in the areas that are darker or brighter on the film itself. All right, let me just delete this one now that we don't need. So since this is a hardware problem here, this is a hardware problem, which is referring to the actual monitor itself, we can't fix the problem in the monitor, and we have to apply the correction via software. So this correction here, this gamma 0.5 correction that is sum on the gamma 2.2 of the monitor, is actually encoded in the files. So for example, JPG, TIFF, or PNG, and a lot of other files. Most of the files, actually, most of the file formats have this sRGB encoding, because that was the only way of visualizing on the screen with this problem the images so that the eye can interpret them correctly. Now, in an LED or LCD screen that do not have this kind of behavior and they are absolutely linear, you do not need to correct the signal of the monitor with this curve, because the problem is that all these files that have been used for ages have all been encoded with this gamma correction, so that you could see the files on the CRTs. And so, since these ones are standards, are image file formats that everybody uses, you can't change them, and either you change them or you go back and change all the images so that you can see them in the LED or LCD monitor today. But then if by any chance you are gonna see any of these images on a CRT screen, then you won't see it correctly. So for legacy problems and to keep compatibility, you can't go and remove these gamma 0.45 correction. So what did they do? They applied this correction in the LCD and LED monitors. So they basically introduced a simulation of the errors that the CRT monitors had in order to then open the files the right way once they are opened via software and they go through the decoding of the file, which means getting the files back to the linear stage. So it's a little bit of a headache, but it kind of makes sense if you think about it to do it this way. Now, the good thing about this encoding is that was pure luck and wasn't something that was studied or designed, is that this kind of response, this kind of curvature here was pretty good to visualize the images, because our eyes have a sort of similar behavior. So we can distinguish better tones in the dark areas than the bright areas. So we don't need as many information in an image in the highlights, for example, because anyway, even if we had a lot of information there, our eyes would not be able to distinguish them. So from a perceptual point of view, so if you only consider what your eyes can see, then you don't need as many values in the highlights as you need in the darker areas, in the shadows, where our eyes are more sensitive and can distinguish more tones. So this kind of response here helps encoding the images so that we have more values between the shadows and the midtones and less values in the highlights there. And this is really important because this makes so that we can encode a lot of values that are useful to the eye to interpret through the brain the image, and use only 8-bit to do so. And this is even more important because most of the screen, even today, are still displaying only 8-bit colors. I'll make another video about the bits so that you can clarify that part as well, but for now you need to know that most of the monitors are 8-bit. Some monitors are 10-bit, the ones that are designed for photography, like the one that I have here. But basically all our digital devices are based on an 8-bit visualization. So what everybody was worried about is to capture the data that the eyes can perceive and elaborate through the brain in an 8-bit format, in an 8-bit resolution. It's a gamma 2.2 curve here that the monitor is using that is putting, as you can see, more values in these areas of the graph. So see, actually these are all basically lower brightness, right? If this is a midpoint, this is a midpoint of the image, most of the values are in this region here, and then a bunch of values are here in this region. So all the values that are here are dedicated to shadows and midtones, and then you have a bunch of values dedicated to the highlights. And the relationship between this curve and the eyes is just luck. So this gamma monitor, gamma 2.2, was not designed because the eyes have this sort of response, but was just the way the monitor worked. So there is no relationship in this sense. It was pure luck that the eyes work in a similar way, and so the two things have been misleadingly related. So I hope this makes sense. These things are never easy to explain, so I hope that this is making a little bit of clarity in your mind why there is a gamma correction, what are we doing to an encoding of the file, and so forth and so on. Now the problem is that in a CG environment where you have, a computer generating an image and is not a capturing device like a camera sensor or a scanner, you have the opportunity of creating a lot of details, a lot of values, a lot of information. You can create 8 but also 16-bit or even 32-bit floating point values and then store them in some sort of file. So it is a waste of information not to keep this data to elaborate the final image that you have there. So it's a limitation in the dynamic range of the images that you will get at the end, because you are compressing everything into an 8-bit image, discarding, as we said, a lot of the highlights and giving priorities to the shadows and the midtones. And when you are working with the images from a mathematical standpoint, the more values you have, the better it is, because you can correct the images more, you can color grade the images more, you can adjust the highlights so that maybe the window is not as bright anymore, and you can do all sorts of operations. So it makes total sense to work in a way where you don't have this encoding embedded in the files, but you have all the values as they come out of the render. Same Same thing when you apply textures to your materials. The textures might have been saved in a JPG or a TIFF file that is a gamma encoding, and so it means that some values of those textures have been thrown away. Now, if the texture has been captured from a camera and has been saved in JPG, the values has been already thrown away because the camera is encoding the JPEG image, and so it's throwing away the data according to what we said. But if you are painting the image yourself, you might have more chances of having a higher dynamic range, and you don't want to have to discard those values just because we want to limit them into a file that is only 8-bit. To overcome these problems, there are other file formats that can record in higher bitrate, 16 or 32-bit, and the most commonly used one is the EXR file that basically does not have any gamma encoding, is a pure linear file, and this is used in visual effects and CG. Because of this reason, because it's not a limited file, you have all the information as they come out of the render. In terms of photography, for example, or cinematography or film shooting, you have the RAW file. A RAW file is pretty much like an EXR file, except that the EXR has very specific standards, has multi-channels, and has a lot of different things that we'll see in a specific lesson on the file formats. But the RAW files, in a way, is just a file that records the information that the sensor has captured. So the RAW file is also a linear file because it is only embedding the information of the camera without limiting the information into an 8-bit file with this sort of gamma correction. We'll do another video where I explain more in depth exactly what happens when you use an 8-bit textures or a 16-bit EXR textures in a CG environment, in a 3D environment, so you can understand what are the real implications from a CG point of view. But this was more so that you are aware of what are gamma correction, why we need a gamma correction, and what does it mean exactly. Thing that I have to say is that these files are linear per se, but the monitor is only 8-bit. So another thing that you need to do now, assuming that this operation is gone because we don't need to worry about encoding the files in a specific standard that does not meet our requirement because we want more information, and because we don't have this problem with the hardware, but we still are limited to 8-bit output of the monitor, or in the best case is 10-bit. Now we need to have something that shows these images correctly through our screens, which is called a LUT. A LUT, or Lookup Table, is nothing else than one of these sort of functions applied only when you display the image, so it's done via software, to these images, so that the values that you are elaborating are all the values of the 16 or 32-bit, but then these values are then compressed for your output, which can be the screen that you're working on, that we are working on now, that can be the television, the projector at the theater, but what is important is our files still retain all the information, and you can always come back and adjust things and operate on those files without losing information as you would if you were using this kind of files. So I hope this video wasn't too boring, and I hope this clarifies a little bit all these difficult things like gamma corrections and gamma encoding and raw and linear files. And if you found it useful, please hit the like button, subscribe to this channel, and hit the bell next to the subscribe button. And also leave me a comment. Let me know what you think. Let me know your questions. Interact with me. I'm happy to reply to all your questions. And if you want me to make a specific video on something, I will be happy to accommodate if it's possible. And I think that's it for now. I will see you in the next video. Bye.